All right, continuing 1.3, let's talk about measures of variation. In the last part of 1.3, we talked about population, statistics, parameters, samples, and then measures of central tendency, mean, median, and mode.
Justin Spalding, please come to the front office. Justin Spalding, please come to the front office.
So variation is a term that means we're looking at a number that describes the spread of the data set. Spread has an A in it, sorry. Spread. So in other words, in the last part of this section, we talked about the central tendency. Where exactly is the center? Maybe it's right here, which means in general, the highest point of the data is probably somewhere about in that point. But from there, how spread out is our data? Is our data not very spread out? Is it pretty shallow like this? Or is it really spread out like this? Variation is a number that tells us how spread out, left to right, our data is. We have 4 basic types of variation that we're going to learn about in this class. One of them is range. To calculate the range, you just take the maximum value in your data set and subtract the minimum value. Minimum value. Easy. We like to use the range anytime that we're using the mode as our center. So that's not very often. The next one is variance. Variance is not actually something that we use that often either. The variance looks like this for the population, sigma squared, or this for the sample, S squared. Remembering back in the last part, sigma and S are symbols that we use for the standard deviation. So the variance is the standard deviation squared. The interquartile range is something that we'll talk about in another section. For now, the interquartile range is the third quartile, Q3, minus the first quartile, Q1. We'll talk about how to get that Q3 and Q1 in another section. But we use this interquartile range, IQR, anytime that we use the median as our center. So that would be when we have skewed data or when we have outliers in our data. The rest of the time, when we have nice symmetrical data, we like to use the mean. And anytime we use the mean, the variation that we calculate is called the standard deviation. The standard deviation is the average distance of each value from the mean itself. So on average, how far away are our data points from the average? And then below that, you see 2 crazy looking formulas. These formulas are in your formula sheet, which you can use on your AP exam in a shortened form. Let me pause this and I'll go grab it. All right, so the formula you see on the right, sample standard deviation, this big crazy formula, it looks a little bit different on your formula sheet that's provided during your AP exam. On your formula sheet, it looks like this, and they are actually the exact same formula. Before I get into that though, let me look at this one. As you know, when we're calculating the standard deviation from the sample, we're always trying to make predictions about the standard deviation from the population itself. So, as I said, standard deviation is the average distance from the mean. So what we have in here, quick review, all of these mu's are the mean itself. That's the mean, that's the mean, that's the mean. And this dot, dot, dot here means that there's more in here than just those 3 differences. The x is in here, x sub 1, x sub 2, x sub n. That's every single value within the data set, every single number in the data set. So you can see what they're doing is they're taking the number in each number in the data set, subtracting it from the mean. Take the second number in the data set, subtract it from the mean, which gives us the difference between each data set and the mean. Remember, we want the average distance from the mean. So there's all of our distances from the mean. Now imagine though that half of our data is less than the mean, right? Half the data is greater than the mean. So half of these differences that we're calculating here is going to end up being a negative number, right? Because if it's less than that, if you subtract something less than that, you'll get a positive number. If you subtract from something greater, you're going to get a negative number. And when we add positive and negative numbers together, we're generally going to get just pretty close to 0, right? Positive something plus a negative something is 0. So to avoid just adding things together and just getting 0, we square those numbers. When you square a negative number, it automatically becomes positive. You square a positive number, it stays positive. So to avoid adding positive and negative numbers together, to make sure that they're all positive, we square each of these distances, and then at the end, we'll square root it to get back to our average distance itself. Okay, so that's why there's squares and square roots. So in general, we're calculating all of the distances between each number and the mean, and then dividing by the total number of data pieces within the population. That gives us the average distance from the mean, which is called the standard deviation, or sigma. Okay, on the other end here, when we're calculating the standard deviation from the sample, we would expect the same thing, but there's one small difference. This denominator is the only thing that's different. Recall, X bar is the mean for the standard deviation. So it's just like using mu in the population, no difference there. So the only difference between this formula and this one is the denominator. So why are we subtracting 1 from the denominator? N minus 1 is what we call the degrees of freedom for sigma. And the reason why we divide by the degrees of freedom here instead of just the sample size is because when we take a sample, we are seeing less information than we do in the entire population. So think of it this way. In the population, maybe my mean is about here, and my data looks kind of like this. When I take a sample, my sample mean, if it's a good sample, will probably be very close to what the population mean is, about the same height. But since I'm taking a sample and I'm seeing less data, I'm automatically going to see less spread from that mean. So the sample standard deviation, if I calculate it as a true average of the distance from the sample mean, is automatically going to be smaller than the population standard deviation. So to account for that error, we use the degrees of freedom, n minus 1. By dividing by a number 1 less than the actual sample size, we end up with a bigger standard deviation. Think of it this way. 50 divided by 5 is about 10. 50 divided by 1 less than 5 is bigger than that. So it will give us closer to our actual population standard deviation that way, and that is why. You'll get questions in your quiz for this section that simply ask you, what are the degrees of freedom for this sample? All you do is subtract 1 from the sample size, and that's your answer. Some questions really are that simple. Getting back to the sample standard deviation formula on your formula sheet for your exam that looks like this, as I said, that is actually the exact same formula. We can see here our denominator is still n minus 1, our degrees of freedom. And the numerator, remember, if I'm multiplying something by a fraction, we're actually only multiplying it by the numerator. So everything here is what's in the numerator of this fraction. Epsilon, this big Greek letter that looks like an E, epsilon means I'm going to add for every instance here. And x sub I refers to every piece of data within our sample. So I take my first piece of data, subtract my mean, square it, and then I add each of those for every piece of data, just like we do over here. No difference. So again, when do we use a standard deviation as our measure of variation? We use it anytime we want to use the mean as our center. They always get paired together. Range is paired with mode, IQR is paired with median, and the standard deviation is paired with the mean. They just go together. The purpose of our standard deviation of the sample, S, is to give an unbiased estimate of sigma, the standard deviation for our population. In the 1.3.9 practice that you have to complete and then submit to me for grading, this is the first page that you see. Let's go over how to calculate the variances for this data set before you try to do it on your own. So the first one is the range. Calculate the range, the maximum value minus the minimum value. To make that easier, I'm going to go ahead and reorder this data set so it's least to greatest first of all. It doesn't take very long because it's a small data set. 1, 3, 3, 4, 4, 5, 5, 6. Okay, so I can see my maximum is 6 and my minimum is 1. I subtract those and I get 5. So the range of this data is 5. And then it says to calculate the sample mean. To calculate the sample mean, I'm going to add them all together and then divide by the number of pieces in my data set. I'm going to use the space below for that. 1 plus 3 plus 3 plus 4 plus 4 plus 5 plus 5 plus 6 divided by 1, 2, 3, 4, 5, 6, 7, 8 pieces of data. And that is about 3.875. Or not about, it is 3.875 exactly, sorry. So we would say the sample mean, X bar, is 3.875. Okay, C, it says calculate the sample variance and the sample standard deviation. So just to remind you, the variance is just the standard deviation squared or the standard deviation before we square root it. So let's see. The sample standard deviations formula looks like this. And I need to plug in all of our data for that. We have 8 pieces of data, so it's going to end up being really long. I'm going to pause this and put it on here. So that's really long. And now I need to perform all the subtraction and then square each of those differences. And then I have to add everything together in my numerator and then divide by 7 and square root. And I end up with a sample standard deviation of about 1.5526. And I can see my sample variance before I square rooted it was about 2.4107. So there's my two calculations, my two statistics they ask for in part C. So that's obviously a really long process. So I'd like to show you how to do this on your calculator. Of course, on your AP exam, you have a calculator portion and a non-calculator portion. In general, if they're going to ask you to calculate the sample standard deviation by hand, it's going to be a pretty small sample. So you should know how to do it by hand for a small sample, but for large ones, we're going to save some time and we're going to use a graphing calculator.